Thanks for joining us at the P99 conference. I'm honored to be giving the opening keynote on the subject of misery metrics and consequences. This is generally a subject I've been talking about and spending some of my personal time on over more than a decade now. And my own thinking and experience and view of the future actually has evolved over that time. This talk will actually try to go a little bit through that evolution and maybe bring you to where my current thinking is. But we're going to go through some history and some pain before we get there. The title of the slide of the talk that we have today is Misery Metrics and Consequences. I did kind of debate about where to put the punctuation marks here, misery, metrics, and consequences, or misery metrics. But as we go through this, we're going to touch on a few things. I'm going to start with some introduction, some background, a little bit of the world we live in, how I came to it, and what I think about it. We'll dive into one of my pet peeve subjects, which is how monitoring is just broken, and how it's so broken that there's probably no real fixing of it. So there'll be a little bit of depressing content here, but at some point, I'm hoping we'll see some lights and tunnels and some relationship with them, and we'll learn to appreciate some of the misery that we all wallow in. So hopefully this will all make sense by the end of this talk, but looking at the titles that I've had for related talks over the years, I've used titles that are nice and responsible, like understanding latency and application responsiveness, or talking about services and microservices and response time behavior. But really probably the most popular subject that people have followed me on in relation to this is how not to measure latency, and a nickname for the subject in general, and one that you probably can't get accepted into most conferences, is the oh shit talk. And usually I tell my audience in this talk it's okay to say oh shit when you hit an oh shit moment, because there are some, and we can at least enjoy noticing them. I will call out a few of those potentially during this talk. It's awkward to do this over a video stream without seeing your faces and your reaction, but I'll see if I dare do it. But as we go through this, we'll get to some of those oh shit moments. My recent evolution has to do with misery. And I do think that we have some reasons to appreciate and actually benefit from the misery and the metrics of misery that we could look at that relate to this, and that there is some hope in that misery, and that is probably our way forward through all this broken monitoring and measurement stuff. This is a little bit of a pun on the misery thing. How I learned to stop worrying and love misery is a riff off of Dr. Strangelove, for those of you old enough to have seen the movie. And this is not a picture of me. So let's start with just the world we live in. Most of the things that we run on today, that we measure the performance of, that we monitor the behavior of, that we care about the health of, are comprised of services, and more modernly microservices. And we started from systems that were fairly monolithic probably 20 years ago, and those systems have been broken up over the years into pieces. And at the beginning of that evolution, we still saw those boundaries of the original siloed systems. Even though there were services, and even though things could talk to each other, we could sort of recognize the original parts. But as these kind of architectures either evolved, or as brand new things were built from scratch based on service architectures, we ended up with connectivity that looked a lot more like this, and the hope of a clean cloud of services that talk to each other and are able to be reused and scaled and have the right qualities across everything, and the avoidance of redundant pieces of work that do the same thing in different places written in different ways. Now, this is the idealized way we'd like things to work, but as this kind of thing grows and grows and grows, it develops into something that looks more like this. This is actually a picture shared by somebody at Amazon 13 years ago, depicting the Amazon map of microservices back in 2009. So things grow and grow, they become a fairly big mess, and this is the world that we live in, the parts that we watch. When we provide or create some sort of a service that will be successful and scale and serve a lot of things, we need to think about all these other things that might use it. When we are one of these endpoints, we could be affecting and touching so many different services that we can't even be fully aware of them. So when we think of microservices architectures in general, there's a lot of great stuff in them, and there are a lot of great reasons for why we do what we do today. But if you think of this as a microservice, you need to remember that this is what a microservices architecture looks like. And when we look at one piece, and when we measure and characterize and monitor or benchmark one piece, we need to think of its interaction in the whole, whether how its behavior could affect others or how it's affected by the behavior of many external downstream things. Now, as a result of the evolution of service architectures, we also evolved other things that have to do with how services live together in a world that's so complex. One of the key evolutions we've had is a notion of a circuit breaker in various forms. And the purpose of a circuit breaker is not to control the flow or to meter or to make things healthy. It's actually to prevent fires. The original circuit breakers we put in electrical systems are designed so that the circuit breaker trips before enough current runs through a wire to burn down a house. And the purpose of that is I would much rather have my circuit breaker trip and deal with that than deal with a house fire. Similarly, when we apply circuit breakers to services, we protect the service and the ecosystem as a whole from burning down because of overstress, because of overload, and we accept that we're going to cause pain, we're going to push back, we will break things that talk to us, rather than just slow them down. But we do this in order to prevent an even worse outcome, which is a total meltdown of the service framework. One of the first shared or common libraries that introduced the notion of circuit breakers widely in a way that people were able to apply to many, many different services was Hystrix, that came from Netflix and open sourced way back when now. And from there, we evolved into all kinds of other forms of things between services that help us control, shape, meter, and protect services and the framework as a whole. Various service mesh architectures, with probably Istio being one of the biggest ones now. But I really don't like to call out winners or project futures. I'm sure that when we talk about this again in 10 years, there'll be other names up here. But as we build these service frameworks and these meshes that connect them and the mechanisms that they use to talk to each other, we're really building systems that are trying to repeatedly across many services apply the same methodologies of both measurement, metering, and control. And this is a picture from the original Hystrix architecture, and we get these nice dashboards at the time. But since there's so many things to put on those dashboards, more and more visualizations have evolved, and these come from different service mesh architectures. And a big step that we probably have evolved in the last, I'd say, 5 years or so, is sort of the separation of a service mesh control plane from the data plane that connects the actual services and where traffic actually flows, where those control planes could be used both to get telemetry out and to apply control, to reshape things and such. Now, across all this, we have measurements and behavior and metrics. And really, if you look at what we've built here is, we're building a matrix of services that connect to each other with a lot of detail in each, but a lot of detail in the whole. Now, in this world of a matrix of services, I've been playing this annoying role. My role is just to complain and scare you and ask you to remember that all I'm offering is the truth. Now, at this point, if we're in a physical room, I would say you have a choice. You can take the blue pill, and you can keep believing whatever it is you want to believe about how measurements and latencies and P99s work, or we can take the red pill, and we can examine a little bit of the scary stuff and see just how far the rabbit hole goes. This is a bad misquote of the movie, but most people do seem to choose to stay given the title of the talk. So let's start with some of those realities that are unfortunate for us. We all like to look at pretty charts. This is an example of a simple, pretty chart from a monitoring system. Lots of us look at these dashboards. This is from a Grafana dashboard. And usually we end up with lines plotting different things over time with some colors and some summarized stats. And when we look at these, it's worthwhile to examine what we have in front of us and why we have those things, and what value does it add or detract to have them. So in this specific chart, which is from a very common system, we're looking at the percentiles, the 25th percentile, 50th percentile, 75, 90, and 95 of a service over time. The period of time here is about 2 hours. And it gives us some feel, presumably, for what's going on. If we ask an observer what is interesting about this chart, what would you pay attention to, they'd probably take a look at this spike in the middle and say, okay, something happened there, I may want to examine it. And if we did go look there, we would see that the 95th percentile seems to have spiked up for some reason around 1240 and on the time axis. The 90th percentile spiked up a little bit under it. The other percentiles seem to have stayed the same, so that might inform us that there's some outliers, but maybe the rest of it is okay. And okay, maybe we want to go look at the system, see what's going on there. Now, I just intentionally wasted about 20 seconds of your life with what I just described. And unfortunately, these charts are wasting a lot more time of your life by showing you the same information. What we're showing here goes up to the 95th percentile. What is not shown on this chart is the 5% of things that are worse than 95th percentile. They're not shown at all. This chart shows the good stuff. It only shows happy results. For this chart to show even this spike, we had to be so bad that more than 5% of the things that we see have reached this level. This is the chart you show if you want to hide from reality. It's a chart you show if you want to hide reality from other people. It's a great chart to show if you are not doing your job well, but you want your bonus anyway. And it's worthwhile for that purpose probably. But if we want to be honest with ourselves, and if we want to build robust systems, if we want to understand how our systems actually behave so we can get to high performance behaviors without bad behaviors associated with them, we probably want to look a lot deeper. So don't do this. Now, if we do look at a lot deeper and dig a little bit more deeper into the nines, we'll find out that this is from a real world data set that somebody gave me. Okay, we're looking at 95th percentile and some average and median, but if we look at the exact same system and add the P99 to it, we see that P99 is dramatically worse than everything else we've been looking at by orders of magnitude, by at least an order of magnitude here. So hiding from that truth is by definition hiding bad things. It's not just 5% of things that we were hiding, it's the bad 5%. We sorted them, we put the bad on one side, and then we intentionally ignored it. By seeing the P99, we expose an extra 4% of that 5. Now, you might say that's much better, and it is much better, but this chart has the exact same problem that the previous one had. There are still 1% of things, 1% of things that are by definition worse than everything we see here that are not being plotted. So the act of showing percentiles and percentiles only to some depth and only to a few numbers and nines usually is the act of hiding from reality. Now, you might think that projecting from the common case to the outliers is useful. It might give you some good insight to general average performance and to overall throughput. And there are a lot of things you can do that are good with this. But if you do care about service levels, or you care about the behavior of your systems as seen by end users, by customers, by businesses, you need to look deeper than this. I've been talking about this subject, writing about it, doing some open source stuff about it, and blogging here and there for almost a decade. And one of the formats that I don't do enough of, but I've done a little bit of, is to tweet about something under the tag latency tip of the day, and then to post a blog that rants about my own tweet with some actual explanation of what we're talking about. So this is an example, what I think an average is good for. An average is basically a random number, and it's most often used to ignore reality. That's what I see when we measure performance and use averages. But along these lines, I've posted a lot of different things, and this chart that I just showed you comes from one of those. And it's a great chart because there are many things that are wrong with it. I showed you one. P95 is the highest it goes to. But there's another one that's very important to note, and that's the text. When we look at the text in these charts, what we're actually looking at is a charting, a dashboard system that knows how to plot numbers, show them in nice lines, and then plots numbers, shows numbers that are the summary of those lines. Usually we're going to see averages of whatever value we're plotting, because the charting system doesn't actually know what we're plotting. It could be throughput, it could be latency, it could be response time, it could be error counts. It's numbers on a line, so here's the average of those numbers. But if you think through, this average, this 184 milliseconds associated with the P95 in this chart, which is the only number we have associated with the P95 in the chart, what does it mean? What does it mean to average the P95 over a period of a couple of hours? And the actual answer is it means nothing. It's a completely meaningless number. Unfortunately, it's the only number on the screen, so it's probably the number you're going to tell somebody else when they ask, so what was the P95? Well, it looks like it's 184. To exemplify how bad this notion of averaging percentiles is, let's run through a really simple exercise of averaging a very easy to understand percentile, the 100th percentile, the maximum. Now suppose I have a data set that has 15 minutes worth of maximums per minute, and it looks something like this. I observe the maximum every minute, I plot it. I could plot it on Grafana and it'll show a nice chart. And then we average that. And we can say, because I picked the numbers to make this math work exactly, that the average 100 percentiles, the average maximum over the past 15 minutes was 42. Well, great, that's what the math says. But what does it mean? If you look at the numbers, the maximum was never anywhere around 42. It was well below 42, it was well above 42. It was never 42. The maximum over the last 15 minutes is clearly 601, not 42. So if I care about that percentile, the maximum, whatever it is, I probably need to look at the high here. The 42 is just a mathematical averaging of numbers that has no meaning. And the same way you can't average the maximum percentile, you can't average any percentile and be left with a meaningful result. It represents the hope that the percentile in every minute was exactly the same, but then you don't need to average it. You just pick one. So the simple tip from that is you just can't average percentiles. The math doesn't fly. You can't do this. In every chart, and every time you see one of these lines showing P99s, P95s, any percentile, and you see that text, resist the urge to use it. Resist the urge to talk about it. If I could white it out on the screen, I would, but unfortunately, that ruins screens. But as we show it to people, if we plot a chart like I just showed and we give it to somebody else, it comes with the inherent blessing of the number. The receiver of that chart will think that this means something, might believe that it's real, and be misled by the data. So remember this tip. Percentiles have problems, and averaging them have even more problems. Now we're here at the P99 conference, and a natural question to ask is, what percentile levels do you monitor the best? Given the name, we think P99 would be a good percentile to monitor. So let's talk about that a little. If we monitor the 99th percentile of latency or response time of a service, is that a good indicator of what its impact on the world looks like, or what the world might see if this P99 behaved this way? And we can ask the questions in this terms. What are the chances of a single web page view of a single user, or a single interaction by a client or something like that, experiencing worse than this measured number that is the 99th percentile? Now we could ask this about different things in our systems. We could be monitoring or measuring or benchmarking a search engine, and we could say, I'm looking at one search engine node. What are the chances that a web page will see worse than the P99 I have here? Or maybe I'm looking at a key value store of some sort, or an in-memory cache, a database node, some CDN like an Akamai or some other edge service that provides content, or one of your microservices that you're probably measuring. When we measure the P99 in any of those, what are the chances that our end user, the person or the client or the other applications or another service that uses us, would experience worse than the 99th percentile here? Well, I went several years ago and looked at the actual number of HTTP requests involved in going to any of these web pages. And all I did here is point my browser at the web page and count the number of HTTP requests that were generated and came back as a result of my one click of going there. And these are the numbers. Now we could do the simple math from there and derive that likelihood that me, with one click, would see worse than the P99 of any of those websites. And the P99 I'm talking about there is the P99 of an HTTP request, because there are that many HTTP requests. So if an HTTP request had a really good P99, what is the chance of me seeing worse than that? The math is up there, and as you can see, it works out to virtually every website out there has a bigger than 50% chance of seeing worse than the P99. The only website on this list that doesn't have a worse than half chance is the google.com clean search page. And that one is still more than a quarter of occurrences will see worse than a P99. So the tip that comes from that is most of your page loads will experience worse than a P99 server response. So why are we measuring this thing? Why are we spending time measuring something that most things will see worse than? Not better than, worse than. And it's very tempting to think that P99 means 99% of things are going to see better than this. But no, the math works out differently, because your little service, the one thing you're looking at, one of operation at a time, is then multiplied by the number of times it is called, or services like it is called, and how many of those are involved in one operation at upstream. So if we want to gauge actual user experience, we can ask questions like these. If I have a really short user session with just 5 pages, and each one of them was super clean, as clean as that Google search page, so only 40 resources, how many of the end users will not experience something worse than the P95? the math for that turns out to be pretty absurd. 99.997% of people will see worse than this number. So it's a pretty useless number to look at. It's the number everything is worse than. Well, we can make up any number. 0 is just as good. But we can ask the same about the P99. What are the chances, or how many users will not experience something worse than a P99? Unfortunately, in this scenario, that's about 13%. 87% of your users will see worse than this. So is this a good number to focus on? In reality, what this means is you want to see deeper number of nines. You want to see more nines. And you can ask the question of how many nines I need to see in a way like this. If we want to know what percentile do I need to look at, or what percentile will be experienced by 95% of end users in a scenario like this, we'll come out with this number. And if I want to see what percentile will be experienced by more than 99% of users, which is what most people think about when they think of P99, you need this many nines in your results. So if you really are measuring things and you really want to know, measure your outliers or percentiles in a way that lets you know what the real world might experience, you need a large number of nines. And unfortunately, we don't have a large number of nines. Now, why don't we have a lot of nines in our response time and latency numbers? Well, there are all kinds of reasons, and we talked about a few of them, but one of them is you can't average percentiles. You can't accumulate a lot of nines from little delta measurements of other things, and you can't derive an hour's worth of 5 nines from a lot of 10-second P99s. There's no math to derive this from. As a result, and because we tend to measure what we can in a second, 10 seconds, maybe a minute, we only accumulate what we can within that, and often there are not enough data points in the period of time we're measuring to classify them with enough nines. And we don't tend to aggregate things across the data sets in order to actually extract higher number of nines from larger data. And there are things you could do about this. And I have spent a lot of time, more than a decade, building libraries and encouraging people to use them. And I built this thing called HDR histogram that's now available in 9 different programming languages that other people did. And you can use it to record data and to accumulate intervals of data together to get accurate number of nines across a lot of stuff. And it's built for speed and useful in low latency systems. One of the things I'm really proud of is it's actually running in Mars right now on the Mars helicopter. It's gotten that far. But unfortunately, the bad news is I've kind of given up on this being a solution. It's a great solution for people who can and will apply it, but the chances of people actually using well-structured histograms to really extract large number of nines from data is not very high. We haven't seen a shift in how people actually monitor and measure systems in the decade that we have. I know many of you in this conference probably do much better than the rest, but as far as what people actually do in the real world, I've gotten to the point where I'm just accepting that we're not going to see high number of nines measured well. Now, beyond that, though, beyond the measuring of high number of nines, there's the problem of measuring them well. There's a problem I noticed, again, about a decade ago that I call the coordinated omission problem. And I do refer to it as an accidental conspiracy because I think we all do it, unknowingly, but everywhere. And to explain what the coordinated omission problem looks like, if you've noticed how I spell percentiles in all the slides up to now, that was not an accidental misspelling. It was actually originally an accidental misspelling, and somebody called me out on it and said, are you intentionally misspelling percentile? And I said, no, that's a Freudian slip, I think. The lie in percentiles has to do with how they're measured to begin with. Even if everything was right, even if we did the right aggregation, even if we resisted the urge to summarize and average them in the wrong ways, the data coming in itself is a problem. And let me show a specific example of how that problem comes to be. Most of us, when we measure response time or latency, are going to do it by taking time before an operation, taking time after an operation, subtracting one from the other, and deriving the amount of time that we spent doing something. This piece of code comes from an old version of Cassandra. This is how Cassandra measures its own response time. This code has evolved quite a bit in the decades since I've copied it from Cassandra code, but it has a lot more lines in it, but pretty much does the exact same thing. There isn't much else we can do from within a service to measure response time. We take the time before and after an operation, and that's all we can do. So what's wrong with that? Well, the biggest wrong is that long operations only get measured once. When we're doing something long, we measure the length of that one long thing, but the other things that are coming and waiting for us to execute them are not, the start point doesn't happen until we pick them up after we've done a really long thing. So the long operation gets measured once, even though there may be 1,000 things waiting in line. And when those things wait in line, they're going to look really fast. They're going to start the time from when they were picked up, not when they came in. Beyond that, any delay that happens outside of the timing window, if this system was also doing something else, it was busy with writing instead of reading, or reading instead of writing, then we wouldn't even see one bad measurement, because there'll be a bad measurement somewhere else, but not for this step. Now, these two things combine in load generators and in monitoring systems and in self-monitoring systems to give us very false information about percentiles of response times and latencies. The things that we measure are not what our clients will see. And to depict this, I've been using this example for a while, and for those of you who have seen these talks, you might recognize the example, but let me go through it quickly. How bad can coordinate omission be? It's not just a little bit of noise. Let's take this hypothetical system, and let's assume a system that was perfect, that easily handles 100 requests a second, does each and every one of them in a perfect 1 millisecond with no outliers whatsoever. But then after 100 seconds of doing that, we just stall the system as a whole and make it stop. Then after 100 seconds, we'll let it go again. Now, this is the reality that I'm describing, a real system that might do this. And the question is, how would we characterize, how would we measure, what would we report on a system that looks like this? And if I were the owner of this system and I was looking at a reporting of percentiles, behavior, that kind of stuff, I would probably say on the left, the average is 1 millisecond. That's pretty easy. On the right, the average of 50 seconds. Well, it's between, it's 100 seconds of doing nothing, then that's so about 100 seconds over the next 100 seconds. The overall average of these is 25 seconds. The average response time across all this is 25 seconds. And I can also say things about percentiles. 50% is really good. Then the rest is not so good. And the 4 nines here is very close to 100 seconds, because obviously that's what's going on. This is what I would expect a reporting system, a monitoring system, a benchmarking system, a load generator to tell me if they were measuring or monitoring this system. But let's see what they actually do. If we actually measured the way most systems measure, we would get 10,000 results in the first 100 seconds, at 1 millisecond each. Then we'll get this one big result of 100 seconds in the next 100 seconds. And then we're done. This is our data. We will then do math on this data and compute an overall average of 10.9 milliseconds. That's a little better than the 25 seconds that we know it is. And we would also report some really good percentiles. The 99.99 percentile of this system is 1 millisecond. It should be 100 seconds. We know it's 100 seconds. We know it's stalled for 100 seconds, but our monitoring system is not going to say that. It's going to give us a 4 nines that's really good. In reality, what we should have done is actually measure even when the system is stopped. Because if I'm measuring 10,000 results in 100 seconds, I should be measuring 10,000 results in any 100 seconds. I should not be coordinating with the system, stopping my measurement when the system is not happy with me measuring it. And if I did do all this measurement, I would get the results that I expected. We would get the 99th percentile that's close to 100 seconds and such. Coordinate omission effectively erased a lot of bad results and selectively erased a lot of bad results, because when the system was stalled, it wasn't measurable. And when things were not being executed, they weren't being measured. And left us with a much brighter picture than reality for our system. Now, sometimes I'll talk to people and they'll say, okay, I get it. It's wrong, it's noisy, I can't trust the number, but I can at least trust the trend. Better is better, worse is worse, right? Well, better can actually look worse. If we took this system that was stalled for 100 seconds and improved it dramatically, where instead of stalling for 100 seconds, it would answer every request during that 100 seconds. It'll take a little longer. It'll be 5 milliseconds instead of complete stall. It's not as good as before, but it's much better than stalling. And if I ran a measurement system on this, a monitoring system, plotted it nicely on Grafana and looked at results, I would get these results. These results say that whatever it is I did to improve the system didn't do what I think it should have. It took results that were 1 milliseconds at the 4 nines and changed into 5 milliseconds. It made things 5 times worse than they were, so we should probably go back to the original system that was much better. A better system can end up scoring much worse, and a worse system can score a lot better. In fact, the secret to benchmarking in systems like this is to make your pauses as big as possible. If you're going to pause, pause big. Don't play any of those little tiny little pause things. Those just show up on monitoring systems. If you're going to stop, do a big stop, clean up everything, then go fast, because people don't know how to measure stops. Okay, so things are bad. And we have systems that instead of measuring actual latency and actual response time, report the internally focused measurement of how long it took them to do something, rather than an externally visible metric of how long does it take to get something done with the system. And if we actually plot these in the real world, we see huge differences between what service time and internal perception looks like and what response time or latency and what other services would see. And, you know, some people in the real world or the virtual world react with interesting words to that. The notion of red pill and blue pill for this talk came from this tweet, by the way. So if things are so broken and we just can't seem to get anything right here, what do we do? I mean, how does the word even work? You know, at this point, you know, after a decade of trying to explain to people what's wrong and maybe how they should do better and seeing that nothing changes, should we just give up? And the answer is partly yes, give up on some of it, but partly it's not as bad as you think, or it's not as bad as I thought. And a lot of it has to do with some differences between what should be the right way to do things and what people actually do, and the damage that doing the wrong thing can or can't do. So here's some nice pictures of lights at the end of tunnels and rainbows at the beginning of them. And in general, the thing that I would highlight is the world works because something we do works. Not everything we do works. In fact, much of what we do is complete nonsense. It's useless. It's a total waste of time. It's distracting, and it sends you in the wrong direction. But there are some things that we do that work. And if we didn't do them, the world wouldn't work. So the amazing thing is we actually do some things right. The challenge is most people don't know which of the things that they do are the right things. And this is where I'm hoping to shed a little bit of light on things. And this is where misery metrics come in. It's my belief that there are metrics that we do measure that are hard to get wrong and that are responsible for the world actually working. And then unfortunately, the P99 is not one of those metrics, and most percentiles aren't. So where are those metrics? What are we doing that actually seems to work? Well, within a modern DevOps pipeline, we can look at the monitoring side and look at what people actually measure there. And I just gave you 15 different reasons why what they measure is nonsense, is wrong, is misleading, is looking in the wrong place. But there are some things they do that aren't that. And I often look at the role here sort of like a doctor, a well-trained professional that went to school and learned about all the practice of how to do DevOps right and what to monitor and what to do and how to react. But imagine they got this degree 5,000 years ago, with the knowledge of 5,000 years ago. And if we think back to 5,000 years with medicine still kind of worked, but, you know, we're more of the witch doctor type. And, you know, depending on where you were in the world and what society you were in, if you got hurt and, you know, you fell down on when you were gathering and hunting and your knee swelled up, you could just try to bear it out and hope that it gets okay. But you might find one of these in your local neighborhood and come to them and pay some tribute and hope that they help you fix it. And what they would usually do is a set of different things. You know, they might do a chant, they might do a dance, they might give you all kinds of weird tasting herbs or things. They might sacrifice a goat, or draw your blood, or do all kinds of other superstitious things. Now, in reality, they would do a lot of things, and most of those things are nonsense. But some of those things actually worked. I would guess the herbs might have helped, but, you know, the bloodletting, I don't know, and sacrificing the goat, I hope, was not the thing that cured knees. In our reality, we face the same kind of choices. We have a lot of metrics. We don't really know which ones work and which ones don't, but we do have evolved practices from our mentors, from our peers, that seem to keep our businesses running, so we do them. And within those practices, we measure a lot of things like P99s and P95s and throughputs and latencies and all the things we love to have fun measuring. But we also measure some things that matter. And those things that matter are what I refer to as misery metrics. In general, when you look at a system, you can look at a system as working or not working. In most systems, when we monitor them, we know how to recognize some additional states, like it's working, but it's a little not perfect, or it's not totally broken, but this is pretty bad. And really, it's this miserable state that is not totally broken, but pretty bad, that we know inherently in any business how to measure and what to do about. It's things like timeouts and retries and failed queries and angry phone calls, loss of engagements and abandoned shopping carts. Those are things that are bad. The business is not broken, but these things are going on. If there's too many of them, the business will break. Every one of those are things that you can count. And they're things that you have a really hard time ignoring. Most businesses will find out which one of those are needed, and if they don't, they won't work. Now, if we look at these measurements and at these metrics, which in production environments are sort of inherent to be able to measure, it would be nonsense for us to ask questions like, was my 99 percentile a timeout? Because that's not data that's interesting. It doesn't tell me how many timeouts I have. It doesn't tell me how well the business is doing. If the 99 percentile is a timeout, that's pretty bad. But if it isn't, is the 99.01 a timeout? We don't know, right? There's a 1% unknown. And most businesses are unable to survive losing 1% of their business every day. Instead, we can ask questions like, how many timeouts did I have? Or if you want to use percents, the right question is, what percent of my requests are a timeout? Maybe it's 89, maybe it's 1.01%, which would have made the 99 percentile timeout, or maybe it's 0.99%, in which case the 99 percentile would have looked perfect. Maybe it's 0.3% or 0.1% or whatever number it is, but it's usually a metric you can go back and ask the business about. If we lost, 0.01% of people today, would that matter? Maybe not. What if it was 2%? What if it was 0.5%? If we can measure the bad things, count them, and talk in percents of things that are bad, not how good is 8%, but what percent is bad, we can actually focus the measurements on the things that seem to matter, that seem to control things. And in reality, all businesses that monitor things react to abandoned shopping carts or loss of engagement or angry phone calls because they can't help reacting them. This is what looking at misery in a monitoring system actually looks like. You measure things like your work and you measure your success rate. The success rate here is plotted as on the y-axis on the right. It's the top 2% of success rate. So from 98% to 100% success, and you can see the success here fluctuating as load grows. Success rate seems to drop. It recovers when you're quiet. It's doing some expected stuff. But this is how you monitor a misery metric. You plot the bad thing and you watch it. And you see how it reacts to the world, and you see how it reacts to load, and you might point your engineers at it and say, can you make that success rate better? That success rate is not the P99. It's not the 5 nines. It's simply how many things are not broken, or conversely, how many things are broken. Every business, every system might have a different success rate. Your SLAs for the service, for the section, for the cluster might be different. But in general, in every place, you know when things are not good enough. If you don't get a result within 50 milliseconds, they'll do it without you. If you don't let them check out of their shopping cart in 5 seconds, they'll go somewhere else. You know those numbers, and you know what good or acceptable is, and you know what bad is. And usually being much better than needed is not a benefit. Being even a little worse than needed is enough to lose business. So my message to you, and as you think through the rest of the show, hopefully you'll keep this in mind, is focus on measuring misery. Think of what misery looks like in your systems. Whether it's a timeout or a long response time or an error of some sort, or a failure of a cluster node, or whatever it is that misery looks like, and count those, measure those. Don't hide them. Always put them up front. And you can keep measuring those other things. You can keep measuring the P99 of response time, and we could keep doing dances and sacrificing goats for fun if we want to. But the ones that matter are the misery metrics, and my advice to you is focus there. When you do it on your system, remember that it's part of a bigger system, and learn to love it. Learn to love the misery that we dwell in. The one last tip of the day I would summarize this as is don't aim to make a specific percentile acceptable. It's what we've been doing for decades. Don't do that. Don't aim to make your P99 a certain number and fight hard to do that. Instead, aim for an acceptable percent of misery. Translate the metrics to what matters and aim and focus on that as you work through a benchmarking of systems or a tuning of system or a re-engineering of system. Focus on these metrics because they're the ones that really matter. So with that, I hope you enjoyed the talk, and I hope you enjoy the rest of the show today. I look forward to hearing from any of you. It's a subject I am passionate about, and reach out to me on Twitter and elsewhere, and LinkedIn under this handle. Thank you very much.